Hi folks, and welcome to Unit 3, Lesson 3. All right, so let's just take a look at what we've seen so far and give a bit of a spiel here that we've looked at different characteristics of functions, in particular domain, intercepts, discontinuities, the sign of the function, the end behavior, and that's where we ended off in advanced functions. And now with our calculus tools, we saw that we could look at when a function is increasing or decreasing, and that has to do with the first derivative. And then we finally have a way to determine those local extrema. And in fact, again, we can use the first derivative again, determine where it's equal to 0, where it doesn't exist, and then see if there's a sign change in the derivative. So in other words, we're recycling those tools of using the sign of a function to give us information. In this case here, the sign of the derivative. Okay, but if you remember in the last thing that we looked at, we had some function that, not the best of Cartesian planes, that we had a function that kind of had a local minimum, which is fine, but then we saw that there was some other behavior that wasn't coming out in our analysis. Okay, this is what I keep calling this sort of squiggly behavior of the function. So it's still nice and smooth, but it seems to sort of snake its way around. So the question is can we get some information about how to determine this behavior, and then later on we'll sort of see how this behavior could be useful in terms of applications. All right, so if you take a look at the examples that I'm going to have you analyze, sort of these two kind of have that behavior that we talked about earlier on. All right, this though kind of almost looks like it's got a cubic behavior, but there definitely is this sort of squiggle, and there's a note here, yet derivative is not equal to 0. And while this one might look like it's out of place, this point that I'm indicating has something very, has a connection to these points that I've indicated on the other two graphs. All right, so what I want you to do is I want you to take a bit of time, okay, to figure out what's going on with the function in a neighborhood of this point. Okay, how are things changing with this squiggly behavior? All right, in particular, what changes? And once you figure out what's changing, does that give you a sense of how you might calculate this point? All right, so I would say take maybe 8-9 minutes to think about this, and then we'll come back and do some analysis. All right, so if you can please shut the video now, take the time to go through the analysis, and we'll come back in a sec. All right, so we're back, and let's see what we can determine here. So I take a look at this point, and I look at the function, and say in both of these examples, I see that the function certainly doesn't change its increasing behavior. Increasing in this case here, increasing here, again, still increasing through this point. So that's definitely something that's not changing. So we have to look a little further. And let's actually focus on the third one, because this characteristic that I'm trying to get to is something that you have talked about in your past. And if you look at just this portion of this function, it almost looks like it's a parabola that's opening upward. Okay, and then you look at that portion of the graph, and it looks like a parabola that's opening downward. And this point seems to be where it changes from opening upward to opening downward. Okay, now this sort of has a very parabolic look to it, but if you look at these two here, well, to the left of this point, it does seem to be curving downwards, and then to the right of this point, it's curving upward. Okay, and similarly here, curving has a downward curvature and an upward curvature. So what we used to talk about opening upward and opening downward with parabolas actually has a more official name, and it's what we call the concavity of the function. Okay, so not surprisingly, you think of the word concave. Okay, concave up, concave down. So the concavity of the function. And what does it mean to have upward and downward concavity? It seems pretty clear here, sort of opens up, opens down. But here we see this curvature downward, and we need a way to define what it means to be concave up versus concave down. I'm sure if I asked you to choose which was which, you'd probably say this is concave up and this is concave down, but we need something more precise. And so guess what we're going to use to define this idea of concavity is we're still going to talk about the tangent lines. Okay, so again, this idea of approximating curves by lines, just comes back to be helpful to us. And if I draw a tangent line to the right, any tangent line, and then I draw any tangent line on the left of that point, and see if we can figure out a relationship between the tangent line and the function in that neighborhood, right? And you may notice that on the right-hand side, all the points on the curve lie above the tangent, whereas here, all the points on the curve lie below the tangent. Okay, and pick, let's take any tangent line to the left of that point, and you see that all the points, well, had I drawn a little nicer there, all the points in that neighborhood lie above the tangent, whereas if I take any tangent on the right, we see they all lie below. And this is how we define concave up and concave down, is if all the tangents in a neighborhood or in an interval lie above the function, like they do here, any tangent I draw, you see that the function lies below it, whereas to the left, any tangent I draw, the function values lie above. So concave up, if the function values are above any tangent, concave down if they're below. Okay, so again, if I draw any tangent, I see that the function values are above it. If I draw any tangent on this side, I see that all the y values are below. All right, and so this is how we're going to define upward and downward concavity. But similar to the way we define increasing or decreasing, while it's very descriptive, I can draw it on a graph and I can see exactly what it means. It's good for describing that behavior. What it's not very good for is figuring out when it's going to have that characteristic. Okay? So we talked about increasing that for any two values, the one on the right had to be bigger than the one on the left. But there was no way to actually calculate or check all of them, but we found a way to use the derivative. And so what we're going to do is we're going to take a little look at how the derivative behaves, not just at any one point, but along a whole interval where we expect it to be concave, in this case here, down. And we look at the tangents and imagine drawing a whole bunch of tangents. Okay, I'm not going to draw them here because it's going to get too messy. But what's happening with those derivatives? Well, I see that those derivatives are decreasing. They're getting less and less positive. And then when I get to this point here, we see that the derivatives are still positive, but they're increasing. So that's interesting. Decreasing slopes. Okay, remember I'm looking at the slopes of the tangents, concave down. Increasing slopes, concave up. Okay, let's see if the same thing happens. This one's pretty similar, so let's take a look at this one here. If I think of drawing slopes, and remember, I always go left to right, I start with a very negative number, okay, because it's very steep with a negative, and it's getting less and less negative. But remember, when numbers are getting less negative, they're actually increasing, okay? Eventually I get to 0, and then they become positive. So again, still increasing. So throughout this whole interval up until this point, the slopes of the tangents are getting larger and larger and larger. And then what happens at this point? They start to get smaller, less positive till they get to 0. And then they start becoming negative. Now, even though they become steeper, they're becoming more and more negative. In other words, the numbers are becoming smaller. And so we seem to have our key, is that when the derivatives are increasing, the function is concave up, and when the derivatives are decreasing, the function is concave down. But think of what we're talking about, though. We're talking about how the derivatives are increasing or decreasing. And what's going to tell us when the derivative is increasing or decreasing? Its derivative sign is going to tell us that. In other words, we're going to be working with the second derivative. All right? because we want to know when the derivative is increasing and decreasing, so we take its derivative to give us that information. Okay, so presumably, if the derivatives have to go from increasing, or in this case here, decreasing to increasing, the second derivative is going to have to change sign. So in this case here, the second derivative is going to have to go from negative to positive. Oops, negative, sorry about that, to positive. Here, if the derivatives are going from increasing to decreasing, that must mean that the second derivative is going to go from positive to negative at this point. And of course, when do functions change sign? Well, at x-intercepts and possibly where the function does not exist. All right, so this is what you're going to look at in the next section here, is you're going to look at some examples and see if our conjectures make sense. Okay, so first of all, when it's concave up, okay, is the derivative increasing, and when it's concave down, the derivative is decreasing. And then if you look at number 4, you're going to compare to the second derivative, and does the sign of the second derivative seem to give you concavity? Okay, so I'm going to ask you to look at these functions and answer 3 and 4, and then we'll come back together before we come up with our algorithm for determining concavity. All right, so take some time to go through these functions, see what you come up with, follow the instructions carefully. I'll be back soon. Okay, so please shut the video down now. All right, so we're back, and I've got Desmos ready to go here. So let's take a look at that first function. Okay, so there's the function, and I'm going to approximate here and just use my good judgment to see where it's concave down and concave up. Well, it seems to be concave down up to about maybe 1.5, somewhere in this neighborhood. And then at some point, it starts to become concave up. So again, let's take a look at our tangents. Our tangents are getting less and less positive. So they're decreasing, then they're going negative. So they're still decreasing, decreasing, decreasing. And at a certain point, again, somewhere around here, they start getting less negative. So increasing, increasing to 0, and then eventually increasing. All right. So let's take a look at the first derivative and let's see what happens. Well, look what happens around this point. The derivative goes from decreasing to increasing. Okay, exactly what we expected. And now if we take out the first derivative and look at the second derivative, well, what did we anticipate? That it should be negative where it's concave down and positive when it's concave up. And let's take a look at the second derivative and we see, yep, right around this x value where we anticipated, it changes from negative to positive. Excuse me. So it looks like we have a way to determine concavity, and it's going to be through the second derivative. Okay, the sign of the second derivative. So let's just look at the other ones just to, check it out. So here we've got a parabola. Okay, good old parabola, and we realize, well, wait a minute. A parabola, this one here seems to always be concave up because it's always opening upwards. Draw any tangent line, and the function always lies above that tangent line. And so what happens when we draw the first derivative? Well, we see that the first derivative, well, it's this line. It's always increasing as we expect. And then if we draw the second derivative, which of course it's just constant, but it's always positive. All right, so this is all fitting our conjectures. And let's take a look at this last one. Maybe this one will be a little more interesting. Okay, oh yeah, this one's a little more interesting. So let's try to figure out here. So it definitely seems to be concave down, still somewhere here, and then it starts to be concave up. And then again, somewhere here, concave down, and then at 0, it seems to change to concave up. So I think I'm actually going to go straight to the second derivative and see what happens. And we see that, well, it's negative, so concave down. Then right around this point, it goes from negative to positive, and it goes from concave down to concave up till around this point here, where it goes back to concave down, always negative. And then once we go past 0, the second derivative is positive again, and the function is concave up. All right? So we seem to have that thing we're looking for. Okay? So let's now go back and write an algorithm for determining concavity. Okay, so step number 1, and this is going to look a lot like our algorithm for determining the increasing and decreasing behavior. The only difference is we're going to be working with the second derivative. Okay, so step number 1 is to find the second derivative. Step number 2 is determine where the derivative is equal to 0 or does not exist, because that's where we know the sign can change for any function. Step 3, test the sign or the signs of the intervals produced by the x's in 2. All right, and lastly, we can then analyze that if the second derivative is positive, we have concave up, and if the second derivative is negative, we have concave down. All right, and what this is going to do is it's going to give us yet more information that we can use to sketch the graph of the function. And of course, it might be useful for other things. All right, now, before we actually move on, okay, to use that second derivative, well, in the same way that we had our points where you have a local max or a min, okay, which in this case here, it's an example of a critical point, so where the derivative is equal to 0 or does not exist. So in this case here, there's a critical point, there's a critical point. We have local maxes and mins, all right, although sometimes you might have a critical point that does not give you a max or a min, like a cubic. In fact, a cubic, hey, doesn't that look like you've got that squiggly behavior where you're changing from concave down to concave up? Well, these points where you have a change in concavity have a name, okay? It's what we call a point of inflection. All right, so if we take a look at all these examples from the first page, all of these represent points of inflection, okay, where we change here from concave down to up, concave down to up, concave up to down. All right, so I want you to take just a minute to think about something interesting that I'm posing here, because I'm changing from concave down to concave up, concave down to concave up, yet I'm saying that this point is a point of inflection and this point is not a point of inflection. So take a minute to just think as what in the world does it take to be a point of inflection? Okay, so shut off the video and we'll be back in a minute or two. All right, so we're back, and hopefully you notice that the difference between these 2 points is here, this function is smooth around that point, whereas here we've got a cusp. There isn't that smooth behavior. In fact, this function here is not differentiable at 2. All right, so what does it mean to not be differentiable? It means I can't draw a tangent line, okay? Now you might sort of say, well, why don't you just say it can't be differentiable? Like here, differentiable at that point. So we can call it a point of inflection. It's got this smooth behavior. Yet here, not differentiable, so we don't call it a point of inflection. Okay, except there's another type of point of inflection where the derivative might not exist. And so now, while we just got back, I'm actually going to ask you to go think of number 7. Is it possible to have a point of inflection? In other words, what do we want a point of inflection to do? To change concavity, but it needs to change concavity in a nice, smooth way, not this jagged way that a cusp might do. Okay, so think about what it would look like to have a nice smooth change of concavity, but having a second derivative that doesn't exist. Okay, so take a couple of minutes to think about this, see if you can draw something interesting, and again, we'll come back in a couple of minutes. So please shut the video now again. All right, so we're back. So what does it mean to have a nice smooth transition from one concavity to another, but have a second derivative that doesn't exist? So I'm hoping that you would have drawn something like this. Now, this is clearly changing concavity from concave up to concave down. It's definitely doing so in a nice smooth manner, but if you see, the tangent line would be something vertical. In other words, the derivative doesn't exist because the slope of the tangent is undefined. So how can we define this point of inflection if I can't just say, well, it needs to be differentiable there? So it has to have a change of concavity, but also needs to be differentiable there. So what we do is we get around that by saying that the function has to have a tangent line at that point. All right? Because that then includes this scenario where there is a tangent, there is this smooth transition, but it just so happens that the slope of that tangent is undefined. So this is a point of inflection because the concavity changes and I'm able to draw a tangent line at that point. This is a point of inflection because it changes concavity and I'm able to draw a tangent line at that point. This is not a point of inflection because there's a change in concavity, but I can't actually draw a tangent line at that point. All right, so I think what we'll do is just before we close up shop here, forgot to do that last time, is let's look at the notes here. So just a reminder of what it means to talk about concavity. So there's our descriptive definition of concavity, which says that if the function lies above all of the tangents in that interval, it's up. If it lies below, it's down. And then there's the more user-friendly version, which says that if I can show that the second derivative is positive, then in that interval it's concave up. If the second derivative is negative in that interval, then it's concave down. And this is what leads to our algorithm. Find the derivative, determine the zeros or points where the second derivative, find the zeros or the points where the second derivative doesn't exist, test the sign, and then once you know the signs, you can apply this note to determine whether there's changes in concavity. All right. And the last thing is this definition of point of inflection. So it's a point where the concavity changes. That's number one. Okay, from up to down or down to up. But the function must have a tangent at that point, even if it's vertical. Okay, so when we talk about point of inflection, we're talking about a smooth transition in concavity as opposed to a cusp, which would not be a smooth transition. So we don't technically consider that point of inflection. So a couple of things. Points of inflection may occur when the second derivative is zero or doesn't exist. Notice it says may occur. The second derivative being zero does not guarantee a point of inflection. So if you look back here, if you were to take something like y equals x to the fourth, and you found the second derivative. So y equals x to the fourth. The derivative is 4x cubed, and the second derivative is going to be 12x squared. Well, look at 0. The second derivative is equal to 0 at 0, but there's no change in concavity. Okay, so similar to looking for local maxes and mins, just because the second derivative is 0 doesn't mean it has to have a point of inflection. Okay, and the other thing to keep in mind, this is often a mistake that's made, is points of inflection do not necessarily occur at critical points. So if we look at our original examples, in this case here, the point of inflection happens to also be a critical point, meaning the derivative is 0 there. But if I look at this example or that example, I have a point of inflection, but it's not a critical point. Okay, so if you've got time, start on the homework, and that's it for this one.